All right, so Unit 14, we're looking at nuclear chemistry. We're going to be looking at how elements change in order to become more stable. And we're going to look at particular elements and the radioactive decay that they go through in this unit. So first thing is looking at radioactive decay. Radioactive decay involves a chemical reaction, and in or dealing with this chemical reaction, we have atoms which are arranged or rearranged, and bonds that are formed and are broken. Also, with chemical reactions, remember, only valence electrons are involved. That's all we focus on, whether they're being transferred or shared. Small amounts of energy are involved. Okay, so when dealing with that transfer or intermolecular forces or intramolecular forces, we do have small amounts of energy there. And reactions can be influenced by external variables such as temperature, pressure, and so on and so forth. Some things that we talked about throughout the whole entire year. So outside of our chemical reactions, we have nuclear reactions. So nuclear reactions, in this case, elements and isotopes change their identity. This is called transmutation. So when I think of transmutation, I think of the X-Men and mutating, becoming something different. Electrons, protons, neutrons, and even some other particles that we're going to learn about called alpha particles and beta particles are involved during this type of reaction. Tremendous amounts of energy is involved in nuclear reactions. We use them to power cities, we use them to blow up cities. We have a lot of energy that's involved there. And the last part is they're not affected by temperature or pressure. External conditions really don't have an effect on a nuclear reaction, and especially in regards to temperature or pressure. So when we look at radioactive decay is based off from radioactivity. Radioactivity is a natural or spontaneous decay where the nucleus of an atom emits a particle to become more stable. As you can see in the diagram off to the right hand side here, you can see that we have alpha, a beta particle, or even gamma radiation is produced based off from this natural or spontaneous decay. When we look at this strong nuclear forces, this is the big underlying principle of why there's so much energy that's involved dealing with radioactive decay. Inside of the nucleus, we talked about this strong nuclear force in previous units. Remember that the neutrons act like the glue that hold the nucleus together. There's a very strong force there, and based off from that force, it takes a lot of energy to overcome that force. When we look at radioactive decay, again, we're looking at different types of particles. And you can see in this diagram below, we have different types of particles have different amounts of energy. So when we look at this, we have alpha particles, beta particles, gamma rays or X-rays, and then we have our neutrons. When we look at these different types of nuclear particles, per se, we're going to be looking at what they change. So the first one that we're going to talk about here is an alpha particle. An alpha particle is like a helium nucleus. Why? Because it's positively charged, it has a low penetrating power, and it has a low health risk. And the mass is about 4 AMUs. So an alpha particle is synonymous or the same as that of a helium nucleus because it has 2 protons and a mass of 4 AMUs. The second particle here is the beta particle. Beta particle, okay, we denote with a B with a negative sign. This is B, the Greek letter for beta. And it's the same as an electron. This electron is negatively charged, it has a medium penetrating power, and a medium health risk. Gamma radiation, all gamma radiation is, or gamma, is energy. It's a high penetrating power and it has a serious health risk. Gamma radiation is not good for you. Typically when you have transmutations or mutations as a human or cancer, this is caused by that gamma radiation. So when we look at radioactivity, when we look at this, if an atom is naturally radioactive, the reason behind this is that the proton to neutron ratio is too high. The belt of stability, as you can see in the diagram shown to the right hand side, shows you that nice ratio between protons and neutrons. You can see as you deviate from the belt of stability, you become radioactive. Another reason is that the nucleus is too big to hold everything together. Any element that has an atomic number over 83 is actually considered to be radioactive, and that the nucleus will actually break down to become an atomic number less than or equal to 83. Really the focus is on 82. We focus on lead 82. because of that fact of stability. So when we look at radiation, one of the biggest things that contributes to radiation, again, is the penetration power of these different particles. So you can see here, alpha particles, they can be stopped by a sheet of paper. A beta particle can be stopped by a layer of clothing. Gamma radiation is by several feet of concrete or a few inches of lead. That's why when you go to get an X-ray, you use lead padded protection to disallow the gamma radiation to the areas in which the X-rays are not being given. So spontaneous nuclear decay reactions. Really all a spontaneous nuclear decay reaction is focusing on the stability of the isotopes, and it depends on that ratio again between the protons and neutrons. So we're looking again at the belt of stability, and we're looking at that ratio between protons and neutrons. An unstable nuclei will emit radiation in the form of alpha, beta, or positron emissions. Stable isotopes have a ratio of protons to neutrons that are about 1 to 1 or very close to 1 to 1, if not 1 to 1. That's kind of like the golden ratio for a nice stable element or isotope in this case. Pb, again, is the largest relatively stable element, again, saying that relatively. Many large radioactive elements will actually decay into that lead, and we focus on lead, which is atomic number is 82, and we focus mainly about lead 206. So, dealing with radioactive decay. Taking a look at radioactive decay and what it actually looks like, you can see here we have a couple different elements, and we actually have a decay particle. So when we look at radioactive decay, we have to focus on the transmutation. Again, transmutation is the changing of an atom's nucleus to a new nucleus. So it's like going back to the X-Men analogy. You're being mutated, you're changing, and by changing you create something new. Transmutation is the changing of an atom's nucleus, but we have natural transmutation, which means that you emit particles spontaneous, and we're going to use table O to refer back to that. Artificial transmutation is caused by humans. We have two types of artificial transmutation. We call that fission, is like division, or fusion, to fuse things together. And we're going to talk about those in a later on video. So looking at table N, you can see all the nucleides and the half-lives that are arranged with those specific nucleides. As you look at the half-lives, you can actually determine the decay mode, which is going to be our focus right now. As you look at your decay mode, you know what's going to happen to this nucleide based off from the decay. So, for example, if I'm looking at gold with 198 as the mass, and I emit a beta particle, okay, so that B minus, if I look at table O, using table O, you can see that, a B minus, a beta particle, is the same as losing an electron. So what does this look like when you're balancing equations? So looking at this example, or particular examples, first one we're going to look at here is the natural radioactive decay of Ra-226. So looking at table N, we know that the decomposition of Ra-226 is that of an alpha particle. Using table O, we know an alpha particle has a mass of 4 and an atomic number of 2. So when we solve these questions here, we want to set the top number, or the mass, equivalent to itself, and we want to set the atomic number equivalent to itself. So what we can do here is split this down the middle. And we're going to look at this. So we don't know that Rn was the product, but looking at this, we know that Ra has a mass of 226. And if we're already at 4, what number do we have to add to get to 226? Would be 222. So we know the mass of whatever this species is going to be as a product is going to have a mass of 222. So figuring out what the element's identity is relies on the atomic number. So we know that we started with 88, and since we emitted an alpha particle, we know that we're already at atomic number of 2, and to get to 88, we have to add 86. Well, who owns the rights to 86 is the symbol Rn, which is going to be our end product. So again, 4 plus 222 equals 226, and 86 plus 2 equals 88. So, looking at another example. So we're looking at plutonium-239. As we look at plutonium-239, we use table N to determine the decay mode. The decay mode for plutonium-239 is that of an alpha particle. So we know that we are already at a mass of 4 and an atomic number of 2. Again, separating our mass and our atomic number, we can solve this algebraically or with just mental math. So if I'm at a mass of 4 and I have to get to 239, I know my remaining mass must have 235. If I have an atomic number of 94 and I'm already at 2, I must have an atomic number of 92. Figuring out the symbol, who owns the rights to number 92 would be that of uranium, so I know that this symbol here is going to be the U for uranium. Looking at another example, I have potassium 42. Again, using the same methodology, splitting the mass and the atomic number, I have a mass of 42. Using table N, I know potassium 42 only emits a beta particle, so a beta particle has 0 mass and a -1 effect on the atomic number. So how do I get from 42 from 0? I have to add 42. Looking at 19 as my atomic number, but I'm at -1, so I must add 20 in order to get to 19, because 20 plus -1 is 19. Well, who owns the rights to atomic number 20? Is Ca, and that of calcium. Again, masses are equivalent, and the atomic numbers must be equivalent. Looking at our last example here, I have iron 53. Using table N, I look at iron 53 and I find that that emits a positron. So looking at table O, I know a positron has 0 mass, but a positive effect on the atomic number. Again, setting the tops and the bottoms equivalent to one another, or equal to each other, I'm at 0. So how do I get to 53 from 0? I must add 53. So, looking at the atomic number, I have 26. I'm at +1. So how do I get to 26 from +1? I must add 25. And what symbol is associated with 25 is that of Mn and manganese. So I have manganese 53 as my product from this decay. Basic rules dealing with radioactive decay is conservation of mass applies. Mass of the reactants must equal the mass of the products. And that's why that way separate the mass from the atomic number. The other part is if the atomic number changes, so does the identity of the element. Remember that atomic number goes to a specific identity. We have all the periodic table, each atomic number has a specific symbol. That symbol always is associated with that atomic number. So if the atomic number changes, so does your symbol. Looking at a series of decay over a long period of time, you can see that uranium-238 series. We're actually going to do a lab where you're going to create your own series for a particular element. You can see that I started with uranium-238, and by using table N and table O, you can actually identify what's happening. These long arrows you can see are alpha particles, where the short arrows are beta particles. So how does uranium-238 decay over an extended period of time to lead-206? Well, you can see that it first loses an alpha particle, then a beta, then another beta, then an alpha, then an alpha, then an alpha, and an alpha, and an alpha, and a beta, and a beta, and an alpha, and then a beta, and another beta, and then an alpha. And by the time this series is complete, you're back to being a stable, non-radioactive material, being that of lead-206, which we talked about earlier, being the largest non-reactive element on the periodic table. Just a little joke for you. It says, when I was young, I used to feel so alive, so dangerous. In fact, would you believe that I started life as uranium-238? Then one day, I accidentally ejected an alpha particle, and that's where it all began. Now look at me. Spent old atom of lead-206. It seems that all my life since then has been nothing but decay, decay, decay. So again, just kind of a little joke based off from that decaying of uranium-238 over a long period of time. Again, looking at the decay products of the uranium-238 series, you can see the alpha particles and the beta particles. And if you look at table N, you can actually find most of these elements and their particular mass and see that this is where you get the alpha and beta particle decay from. Next thing we're going to talk about is half-life and how that reacts or interacts with that of radioactive decay.